In this video, we'll be going over successive ionization energies. So it is kind of like what the name implies. This is kind of like a long word, and I get confused by how long the word is. But it's successive ionization energies. So if we break this word down, it's ionization energy, the amount of energy required to remove an electron. And successive means successive electrons. So not just one electron, it's the energy required to remove another electron of the same atom and to keep removing electrons off of the same atom. So that would be like if you were to write like a little chemical equation for that, it would be sodium arrow sodium Na plus one electron. That would be the first electron removal. One electron removal. Okay, another electron removal would be in succession. This would be a successive. So that would mean to take this and rip another electron off. And so our equation would be like that. Okay, but if we removed another electron. So what I'm going to do on this slide is I'm going to present some data of actual successive ionization energies, and I want you guys to try to observe the data, study the data, and then notice. I'll kind of provide a couple of hints here and there, but I want you to try to notice, see what's a trend, what's going on here, and then I'm going to have you on the next slide try to explain this trend that's happening. So let me put the data up there for 3 different elements. We're going to go right down. We're actually going to go across a row. So we're going to go across, what would this be? The third row of the periodic table. So we're going to go, let's make like a little chart here. So for our 1A element, we'll pick sodium. And for our 2A element, so in the next column over, we have magnesium. And in the next column over from that, we have aluminum. And here is the first ionization energy. So the energy required to rip the first electron away from the atom. 495. All of these values are being measured in, so all of these IEs are being measured in kilojoules per mole. If we look at the second ionization energy for sodium, then we have, it takes 4,562 kilojoules per mole. So let's go take a look at magnesium, and for the first electron, it takes 738 kilojoules per mole. For the second electron, we want to take another one off. So to do this for magnesium, it would be 1,451. If we want to remove a third electron, so that would be like taking Mg2 plus arrow, and we rip another electron off, then it would require 7,733 kilojoules per mole. Now let's take a look at aluminum. We have 578. To get the next electron off, it's 1,817. To get the third electron off of aluminum, so to go from Al2 plus, notice this doesn't look too weird. This is actually what it normally does. That one will cost you 2,745 kilojoules per mole. So on the fourth electron, so if we try to remove the fourth electron from aluminum, it's going to cost you a whopping 11,577 kilojoules. So what I wanted to point out, or what I wanted you to try to explain, is this. If you notice the first electron for sodium, the next electron, to try and take the next electron, is nearly 10 times as much energy. For magnesium, to take the second electron is only about 2 times as much as the first electron. However, if you look at the third electron for magnesium, when you try to remove that, it's that looks like it's about probably about 6 times as much. So there's a big jump here in energy. There's a big jump right here in ionization energy. And if you look at aluminum, we have about 3 times as much. Not too bad. The next electron, around less than 2, maybe 1.5 times as much. But the third electron, I'm sorry, the fourth electron for aluminum is that what would that be? Around I can't do math in my head. What would that be? About 5 times as much? Maybe a little less than 5 times. So here there's a very big jump here. So what can we use? What can we use to try to explain what is going on here? So that's what I'm gonna have you guys try on the next slide. So I have um, some steps here for you to try to explain what's going on. So write out the full electron configuration for each atom. So for sodium, magnesium, aluminum. Also draw a full Bohr model ring atom for each of those atoms. And then use Coulomb's law to explain the large jumps in energy. So here's kind of like my last hint. Coulomb's law is this: the binding energy of the electron can be approximated by looking at this equation. K is a constant, Q is the charge, and this is the charge that the electron feels. So it's the charge by the protons of that atom, and times the charge of the electrons divided by r, which is the radius or distance. It's actually the distance between the two charges. So step 1, write out the full configuration. So this won't work if you use the shorthand. You need to write the full. So for sodium, we have 1s2, 2s2, 2p6, 3s1, and then draw the full Bohr model ring. So we would have 3 rings here. Okay, so you need to look at the so we don't have to draw all the little protons. We could just write 11p for protons. On the first ring we have 2. On the second ring we have 8. 2, 3, 4, 5, 6, 7, 8 electrons. And then on the third ring we have 1. Okay, so do the same for magnesium, and then do the same analysis for aluminum. The full configuration, the Bohr model ring, and then use this to try and explain the data that we saw from here. Okay, to try to explain this big jump, and then the big jump occurring on the third electron, and then for aluminum the big jump occurring on the fourth electron. Okay, and that's the end. We'll see what you guys come up with, and we'll go over the results in class.